RF Man here. Today I want to talk about RF transformers and get into some of the details on how they're designed, how they work, and how they're tested. This is going to be a three-part video, and we'll be discussing the three main types of RF transformers, which include a transmission line transformer designed for a quarter wave. We'll be talking about how to design that with a transmission line and also with lump components. So basically we're talking about just using a simple piece of coax as a quarter wave transmission line. Then we'll be talking about a conventional transformer. So that's something that looks similar to this transformer. This is what I use on most of my LDMOS boards. And then finally, the third part, we'll talk about TLTs or transmission line transformers that use ferrites, and that looks like this. This also includes not only the TLTs, but also a bolum. So we'll be discussing that in part 3. All right, I think for this discussion, it's important to understand the characteristics of capacitors and inductors. And what I'm showing here on the top of the screen, this is an equivalent circuit for a capacitor. And yes, of course, we have the capacitor in the center, but we also have equivalent series resistance, we have series inductance, and we have leakage current flowing through the capacitor, which refers to as leakage current. So that's basically the equivalent circuit of most, if not all, capacitors. And on the bottom here, we're talking about the equivalent circuit of an inductor. So yes, we have our inductance, but we also have our equivalent series resistance and capacitance. Now, the important point here is for a capacitor, the inductance is in series, and for an inductor, the capacitance is in parallel. And why is that important? Well, let's take a look at the next slide and we'll explain that for you. So all components have a self-resonant frequency. That's the SRF that I'm showing here. And this is the formula for capacitive reactance. So it's 1 over 2 times pi times frequency times capacitance. So what you see here with the frequency in the denominator, as we increase the frequency, we actually reduce the capacitance. That's what's illustrated here on this curve. And we can see when we reach the resonant frequency, that's where the capacitance and inductive reactance are equal. Okay, recall your equivalent circuit, right? We've got series capacitance and series inductance. So this is the point where the capacitive reactance and inductive reactance are equal, and the total impedance of the capacitor is then just the equivalent series resistance shown here. So if we continue to increase that frequency, then the capacitor actually becomes more inductive. Okay, and we'll talk a little bit more about this when we look at series and parallel circuits. Now, for an inductor, the opposite is true. Okay, it's inductive reactance equals 2 times pi times frequencies times the inductance. So this shows as I increase the frequency, I'm going to increase the inductance. And that's illustrated here until a point where I'm going to reach the equivalent series resistance at the self-resonant frequency. And then as I continue to increase the frequency, the inductor actually becomes more capacitive. So those are the curves for both a capacitor and an inductor at the self-resonant frequencies that you see here. So why is that important? Well, basically when we have series resonance, okay, the minimum impedance of the circuit occurs at the resonant frequency of that circuit. Okay, and basically at series resonance, it acts like a short. So it has low impedance. Series resonant circuits have a low impedance. Now, if we look at the parallel resonant circuit, it's exactly the opposite. The maximum impedance is achieved at the resonant frequency. So parallel resonant acts like an open at the resonant frequency. So again, there's opposite effects here. Series resonance acts like a short, so you have a minimum impedance, and parallel resonance acts as an open at the resonant frequency, so you have maximum impedance. And we'll see why that's important when we design these different types of transformers. Okay, this curve illustrates the same thing. This is just basically for a length of coax and what happens at a quarter wave. And we're going to actually look at some lengths of coax and measure them on the NanoVNA. And you'll see this curve as we go through that exercise. But here we have basically on this side, before the resonant frequency, we have series resonance. And we see when we reach the resonant frequency, the impedance, which is shown here in ohms, is at its lowest point. And as we increase the frequency, okay, and we get to 0 degrees as shown here, and then we continue to increase the frequency at 180 degrees, we have parallel resonance. So the impedance is at its highest point. So series resonance, the impedance is its lowest point. Parallel resonance, the impedance is at its highest point. Here it's capacitive, here it's inductive. Now at 0 degrees, here, the capacitive reactance and inductive reactance are equal and they cancel out. So that's the point where the impedance would be the lowest. That's what we showed with the series resonant frequencies for both components. So that's what it looks like, and we'll actually measure some coax and take a look on the NanoVNA. Okay, so how do we actually use transmission line in impedance matching? This is the simplest form of impedance matching that we can use, but the restrictions are it's only effective for resistive loads, so only where we have a real part, not an imaginary part, and it only works at a quarter wave of the incident frequency, so basically it's going to have a very narrow bandwidth. So how does it actually operate? I'm just going to jump ahead to this illustration here and show that at a quarter wave we're at 90 degrees, and then the signal's reflected back gives us 180 degrees. So just bear that in mind as we go through this slide. So at the operating frequency, the quarter wave line introduces a 90-degree phase shift. Okay, so that's what we just saw in the illustration. That reflective wave travels back from the load, okay, and undergoes another 90-degree phase shift. So here's our first phase shift of 90 degrees, and then it returns another 90 degrees, gives us 180 degrees. So what does that do? Okay, the resulting 180-degree phase shift actually cancels out the reflected wave and basically ensures that we're achieving maximum power transfer. So that's how that works. We have a 90-degree phase shift at a quarter wave, another 90 degrees, and then the two cancel each other out. So for impedance matching, this is the formula that's used, and this is how it's derived. But basically, when you go through all the algebra, it tells us that the characteristic impedance of the line that we're going to use for impedance matching should be the square root of the input impedance and the load impedance. So I'm actually going to work through an example like that. We can use a piece of coax, calculate what the characteristic impedance of that coax should be, and then show how that piece of coax can be used to match 50 ohms to 100 ohms. And remember, it's only for resistive loads and it has a narrow bandwidth. So let's move on. There's what I showed. Now, the unique characteristic of a quarter wave transmission line, and we're going to look at this on the NanoVNA as well, is that when the load side is open, the source side looks like a short. And when the load side is shorted, the source side looks like an open. Now, I know that sounds confusing, but when we look at it on the, with the NanoVNA, I'll be able to show you exactly what that means. But that basically is one of the unique properties of a quarter wavelength of transmission line. It has a dual impedance. It can look like an open, or it can look like a short. So we'll see that on the NanoVNA. Now, I basically designed a spreadsheet, and anyone who's interested in doing these type of calculations and building these kind of transformers is welcome to get a copy. I'm going to leave my contact information in the video comments, and you can basically contact me, and I'd be happy to send this spreadsheet to you. So I'm just going to click out of the PowerPoint presentation and go into Excel. And I know the print's a bit small, but let's see how we do with this. So this allows me to enter in a physical length of coax in millimeters, centimeters, meters, etc. And it will calculate the quarter wave frequency. That's shown here. Okay, and then I can also enter in the frequency on the other side here, and it'll show me the length of coax that I need. So I did this for 4 sections of coax, and let's just go ahead and use the length that's 0.78 meters. So let's just put that in here. I went to 0.78, and it calculates our frequency. Now this, we're using basically a piece of RG316, so I also, in this case, have to change the velocity factor of the coax to 0.69, and we see that the resonant quarter wave frequency is 66.35 megahertz, or I just rounded that off to 66.4, which is what you see here. And we'll go ahead and measure a length of coax and go ahead and test that on the NanoVNA. So just give me a few minutes to set that up, and I'll be back. All right, so now I'm all set up. I've got the NanoVNA and my length of coax. So what's the first thing we said we need to do is measure the length of coax. This is a piece of RG316, has a velocity factor of 0.69, and you can go to any coax chart and look up what the velocity factor is for the coax that you might be using. So this measures 78 centimeters. That's the length that I showed in my spreadsheet. Okay, and I'm connected again to port 1 on the NanoVNA. So let's just move over to the actual measurements. I'm using the NanoVNA software to make these measurements. And what do we see here? Let's just sweep the results. Okay, and what we want to do is measure 0 degrees. That's where the capacitive reactance and inductive reactance are equal. So that would be where the resonant frequency is. But unfortunately, because of the resolution of the NanoVNA, I can measure at minus 180 and plus 180. So if I take the measurement here at minus 180, I'm 65.2 megahertz. And if I go to plus 180 here, 67.6 megahertz. So if I add those two up and I divide by 2, that's going to put me at 0 phase angle, which measures 66.4 megahertz. Now, that's what we calculated for the resonant frequency, the quarter wave frequency. So what did we say occurs? What kind of properties does this quarter wavelength of coax have at its quarter wave frequency? Well, we said when the load side is open, the source side looks like a short. Okay, so it's 0 degrees. Okay, the load side is open right now. And what are we seeing? This is the S11 phase angles. So again, we're at 0 degrees. This is S11Z, so we're measuring the impedance. And we see that at 0 degrees, I'm about 1.2 ohms. So that's basically a short. And if we go to the Smith chart, remember the Smith chart. Okay, the center of the Smith chart's 50 ohms. And on the left side would be a short. The right side would be an open. So we're almost completely shorted there. Okay, and very, very low impedance of 1.2 ohms. Okay, so again, when the load side is open, okay, it's going to look like a short on the source side. The source side would be the side with the NanoVNA, where the NanoVNA is connected. Now, if we go ahead and we short the output, which I'll do right now, off camera, okay, just putting this short at the end of the cable, and we sweep this again. Okay, what do we see? We see at 0 degrees phase angle, okay, which is right there, we see that now the impedance is measuring 1.49 kiloohms. So about 1.5 kiloohms. So that's basically our open. So when the output side, the load side is shorted, the source side, which is the side of the NanoVNA, looks like an open. Okay, now if we go back and remove the short and we sweep it again, and we go back and look at 0 degrees, we see now when the load side is open, the source side, the NanoVNA side, which is our source, is again 1.2 ohms, or basically shorted. So that's how a quarter length of coax works, quarter wavelength. And that's why we say it has unique characteristics and has a dual impedance. So how do we use that for impedance matching? We'll get to that as we move forward in the presentation. I'm going to go ahead and set up another section of coax and go through the same exercise, and then we'll show how the coax can actually be used to match 50 ohms to 100 ohms. All right, so now I'm back. Next, we're going to be taking a look at a length of coax that's 4.65 meters long. So before I demonstrate that on the NanoVNA, let me just take a few minutes and explain how the spreadsheet works. In this row, we enter in the length of the cable, again, 4.65 meters. Here we enter in the velocity factor. So we're using a section of RG58U, which has a velocity factor of 0.66, so that's entered there. And then what's the speed of an RF signal? Okay, basically the speed of light. So it's 300 meters per second. To determine the speed through the coax cable, we take 300 times 0.66, and that gives us a velocity factor of 198 meters per second. So obviously it slows down as it's flowing through the coax wire. And then the actual wavelength would be 4.65 times 4 gives us 18.60 meters. And then to determine the quarter wavelength, we just take the velocity factor, 198, divide by the 18.6, and this gives us 10.6 megahertz. So the answer is in megahertz. So that's what it basically looks like as a step-by-step derivation using the spreadsheet. And if we go to the next slide, we're going to be taking a look at this cable on the NanoVNA. And here we see 0 degrees is 10.6 megahertz, so that's exactly what we calculated. And then we can demonstrate the dual impedance of the coax looking like it's open and looking like it's shorted. So let me go ahead and set that up, and I'll be back in a moment. All right, so I have this set up on the NanoVNA. Again, I'm using port 1, and this is the length of coax, 4.65 meters. And incidentally, I'm using adapters as well to connect the cable to the NanoVNA and also to short the cable. So when you measure the total length, you need to include the length of the connectors as well. So let's shift over to the software, and let's go ahead and sweep this. Now we're sweeping from 1 megahertz to 50 megahertz. So that's what it looks like. And we're looking again at S11, the phase, S11, the impedance, and then we can see where that is on the Smith chart. And again, this shows the real part and imaginary part, but I'm not going to talk too much about this right now. Okay, so again, we have the same limitation on the waveform, so we have to determine what the quarter wave frequency is. So at minus 180, we're 10.31, reading off the table up here, and at plus 180, we're 10.8. So if we average those two, it comes out to 10.6. So what did we say? What are the properties of a quarter wavelength of coax at the resonant frequency? When the output is open, the RL or load, okay, that we will have a short on the source. Okay, so that's measured again at the NanoVNA. So there's our short at 3 ohms. And then we'll go ahead and take the output and short that. We'll sweep this again. Okay, and we see at 0 degrees phase angle. Okay, and that's where the capacitive reactance in the cable and the inductive reactance in the cable are equal, and they cancel out. And there we said, if the RL is shorted, then our source, which is measured at the NanoVNA, would act like an open. And there we have basically 1.1 kiloohms. That's our open. So again, it behaves properly. And we can also look at the Smith chart. Remember, on this side it's open, and this side it's shorted. So there we have the open. And then if I remove the short, and we sweep it again, you see it moves to the other side of the Smith chart, and it shows again that it's shorted. All right, so we looked at 2 lengths of coax cable. We got very good results, matches the calculations using the formula. So now we'll go ahead and talk about how we would actually match 50 ohms to 100 ohms using this methodology. All right, so now we're going to talk about how to use a quarter wavelength of coax to match 50 ohms to 100 ohms. And remember, this is for real part only. So let me switch over to here and quickly show my setup. Again, we have the NanoVNA. I have a different length of coax, which I will discuss in a moment. And then I've got a 100 ohm load on the end there. So we're going from 50 ohms, which is the standard output impedance of the NanoVNA, to 100 ohm resistive load. And here I had to use quite a few adapters to adapt to the NanoVNA and also my 100 ohm load. So you got to measure the full length of the cable and these adapters. Okay, and what we have here is 75 ohm length of cable. So let's talk about that. I'm going to go back to my presentation, and we'll talk about why we're using a different type of coax with a different impedance. So you can construct these transformers with either coax cable or twisted pair. Okay, and again, we talked about a quarter wave transmission line being good for only the real part, resistive loads, and also having a narrow bandwidth. So here's an example if we want to transform 50 ohms to 100 ohms, okay, using a quarter wave. First thing we have to do, and we reviewed this formula on the previous slide, is determine what the characteristic impedance of the coax cable should be. Okay, so characteristic impedance, normally represented as ZO. So ZO equals the square root of our source, which is the NanoVNA, 50 ohms, and our load, which is my 100 ohm dummy load. So we just take the square root of the sum of the squares. We square 50, we square 100, take the square root, and it's 71 ohms, which is RG34U. Now, unfortunately, I didn't have any RG49U, but I have some RG59U, which is 75 ohms. So that's what we're going to use here, and we should get fairly close results with the coax being only a few ohms off. So this is, again, the methodology in my spreadsheet to determine the length. So now I'm going to be using a length of coax that's 1.93 meters, velocity factor 66, and again, here's the velocity factor in free space. Here it is in the cable, 300 times 0.66, and there's basically 4L, and then my wavelength, which is 25.7 megahertz. So this is the exact same calculations we've been doing in the spreadsheet. I just broke it out here in the slide. So I need to know two things. I need to know what characteristic impedance I should use for the coax cable. That's a pretty simple formula based on RS and RL, and I should know the quarter wave frequency. So let's take a look at how that looks. Again, here's the calculation in the spreadsheet. It's exactly what we just did, and we're using 1.93 as our length, and the calculated quarter wave frequency as shown here is 25.7. So let's go ahead and look at that a little closer. Okay, here's what it looks like on the NanoVNA, and we'll go ahead and just scan this real time. So let me exit out of this and go to the NanoVNA, and let's go ahead and sweep this. And pretty much shows what you just saw on the slide. So again, we can't get to zero because of the resolution, so we go to minus 120, it's 24.4 megahertz, and we go plus 180, it's 26.2, so if we average both of those out, it's 25.7, which is here. Okay, and what do we expect now? We're going from 50 ohms to 100 ohms. So at the quarter wave frequency, what would we expect? We'd expect to match the 50 ohms and have a low SWR. Okay, so let's take a look at how that is. Okay, so here I am. I'm looking at, again, S11, the phase. And then here's S11Z, the impedance, which is this marker here. And if I read off of this table, my impedance is 49.6 ohms rounded off. So very, very close to 50. If we look at the Smith chart, we're basically at the center of the Smith chart at the quarter wave frequency. And if we take a look at this table, this chart, it's S11. This is our SWRs or VSWRs, and we can see, reading off the chart here, we are 1.008 SWRs. So we have an excellent match from 50 ohms to 100 ohms using this methodology. All right, we'll exit out of the software and go back to the presentation. Okay, and so here's just the results summarized. Now, you can also use lumped components for your impedance transformation and would also work at a quarter wave. Okay, so here's how we derive the formula. Basically, we want the capacitive reactance and inductive reactance to equal the characteristic impedance of 50 ohms. Okay, and since transmission lines work in both directions, when we calculate the value of C1 and C2 shown here, it's going to be the same. Okay, so what do? We want the capacitive reactance, inductive reactance to be equal to 50 ohms. And then here's our formulas that we should be familiar with. Inductive reactance is 2 times pi times frequency times inductance. Capacitive reactance is 1 over 2 times pi times frequency times capacitance. And if we rearrange those formulas to equal 50 ohms, then we basically put the characteristic impedance for inductance in the numerator and for capacitance in the denominator. And when we calculate those values, we can determine what the values of L and C should be. So that's what's shown here. And also, as part of that calculator, if I scroll down here, here is the calculator. We'll calculate the values of L and C for you using these equations that we just discussed. So I'm going to use the same frequency that we used in the previous example, 5.7 ohms. I'm sorry, 5.7 megahertz at 50 ohms, and there's the value of inductance and capacitance using the spreadsheet. This is all part of the same spreadsheet, so if you'd like a copy, just go ahead and request it. So here's our calculations, and we come up with 310 nanohenries for L, and then for C1 and C2, 62 picofarads. Okay, and we'll go ahead and take a look at the results here. And this is derived with lump components, but it should behave the same way as the quarter length of Coax, quarter wavelength of Coax. So let's take a look at that. Bear with me a minute and allow me to set that up. All right, so here we have a quarter wave transformer that's built with discrete components. Let's just take a closer look at that. This adapter board you can buy online from NanoVNA.com, and it allows you to build different circuits using discrete components. There are also some surface mount pads on the opposite side, so you can use surface mount devices as well. And here's our 300 nanohenry inductor, 310 nanohenries. And here's our 62 picofarad capacitors. Basically, I'm using a 10 picofarad and 52 picofarad capacitor in parallel, which equals 62 picofarads total. So that's the setup there. And let's take a look at this now on the NanoVNA. Incidentally, the software that I'm using here is NanoVNA Screensaver. That's a free download online. So let's go ahead and suite this. And we said that the quarter wave frequency where the capacitive reactance and inductive reactance are equal, that would be at the 0 degree phase angle, is 25.7 megahertz. So again, we look at the lower side, 25.3 megahertz, the upper side, 26.2. If we average those together, it would be equal to the 0 phase angle, which is 25.7, as I showed on the other slide. So this behaves the same way as a quarter wavelength of Coax. We can see with the output or R load open that the input, that's the NanoVNA side, which would be our source, is shorted. So we see 2.35 ohms here. And then if I go ahead and short the output, the input side, the NanoVNA side, should look like an open. So let's sweep that. And we see, yes, okay, that we've got the output side, the load side shorted, so the input side looks like an open. Okay, we look at it here, it's 5.4 kiloohms. All right, and then we open the output side, our load, sweep it again, and it's going to look like, yes, a short. So that's how it works using lump components. All right, so there's the circuit we just tested, the 310 nanohenry inductor and the 262 picofarad capacitors. And here's the slide showing what it looked like on the NanoVNA with the quarter wave frequency being 25.7 megahertz. And just to wrap up here, you can also use lump components for 1/8 of a wavelength, half a wavelength, and other fractions in between. We just demonstrated the quarter wavelength today. All right, so that concludes part 1 of the 3-part series. The next part will focus on conventional transformers, or CTs. RF Man, thank you very much.